Imagine a computer so powerful that it can solve problems in minutes, problems that would take a normal computer billions of years. This isn't science fiction, this is the promise of quantum computers. Traditional computers, the ones we use every day, are incredibly powerful. They have transformed our world in countless ways, from enabling global communication to advancing scientific research. But they have their limits. When faced with extremely complex problems, even the most advanced classical computers can take an impractically long time to find solutions. Enter quantum computers. These machines are not just faster versions of our current computers, they are fundamentally different. They operate on principles that are entirely alien to classical computing. While a classical computer uses bits as the smallest unit of data, quantum computers use qubits. The difference between bits and qubits is profound. A bit can exist in one of two states, 0 or 1. This binary system is the foundation of all classical computing. However, a qubit can exist in a state of 0, 1 or both simultaneously, thanks to a phenomenon known as superposition. Superposition allows quantum computers to process a vast amount of information simultaneously. But that's not all. Quantum computers also leverage another quantum phenomenon called entanglement. When qubits become entangled, the state of one qubit becomes dependent on the state of another, no matter how far apart they are. This interconnectedness allows quantum computers to solve certain types of problems much more efficiently than classical computers. For example, they can factor large numbers exponentially faster, which has significant implications for cryptography and security. Imagine being able to simulate complex chemical reactions in mere seconds, leading to breakthroughs in drug discovery and materials science, or optimizing vast logistical networks in real time, saving resources and reducing costs. These are just a few of the potential applications of quantum computing. The journey to fully functional large-scale quantum computers is still ongoing, with many technical challenges to overcome. But the progress made so far is promising. As researchers continue to unlock the mysteries of quantum mechanics, the future of computing looks incredibly bright. This both at the same time state is the key to the power of quantum computers. To understand quantum computers, we need to take a peek into the bizarre world of quantum mechanics. This is a realm where the rules of classical physics no longer apply, and the behavior of particles defies our everyday experiences. Imagine a world where particles can be in multiple places at once, or where they can instantaneously affect each other regardless of distance. This is the essence of quantum mechanics, a field that has puzzled and fascinated scientists for over a century. This is the theory that governs the behavior of very tiny things, like atoms and photons. At this minuscule scale, particles don't follow the predictable paths we see in the macroscopic world. Instead, they exhibit behaviors that seem almost magical. For instance, an atom can exist in a superposition, meaning it can be in multiple states at the same time. Similarly, photons, the particles of light, can display wave-particle duality, acting both as particles and waves. In the quantum world, things aren't so clear-cut. The certainty we are used to in our daily lives gives way to probabilities and uncertainties. This is because, at the quantum level, particles are governed by the principles of quantum mechanics, which are inherently probabilistic. This means that we can only predict the likelihood of finding a particle in a particular state, not its exact position or momentum. Particles don't exist in one definite state. Instead, they exist in a haze of probabilities. This concept is known as quantum superposition. It allows particles to be in multiple states simultaneously until they are observed or measured. This probabilistic nature is beautifully illustrated by the famous thought experiment known as Schrödinger's cat, where a cat in a box can be both alive and dead until someone opens the box to check. This fuzziness might seem confusing, but it's what makes quantum computers so special. Unlike classical computers, which use bits as the smallest unit of information, quantum computers use quantum bits or qubits. Qubits can exist in superposition, allowing them to perform multiple calculations at once. This gives quantum computers the potential to solve complex problems much faster than their classical counterparts. By harnessing these strange quantum phenomena, we can perform computations in ways that were previously impossible. Quantum computers have the potential to revolutionize fields such as cryptography, material science, and artificial intelligence. They could help us solve problems that are currently intractable, opening up new possibilities for technology and science. The quantum world may be strange and counterintuitive, but it holds the key to the next great leap in computing. One of the most important concepts in quantum mechanics is superposition. Think of a coin spinning in the air. Before it lands, it's neither heads nor tails. It's in a superposition of both states. Similarly, a qubit can be in a superposition of 0 and 1. This allows quantum computers to explore many possibilities simultaneously. It's like flipping a coin and getting both heads and tails at the same time. This massive parallelism gives quantum computers their speed advantage. Another key concept is entanglement. When two qubits are entangled, they become linked in a mysterious way. Measuring the state of one instantly determines the state of the other, even if they are light years apart. Einstein famously called this spooky action at a distance. Entanglement is what allows quantum computers to perform operations that are impossible for classical computers. It's like having two coins that always land on the same side, no matter how far apart they are. Building a quantum computer. Building a quantum computer is, well, a formidable challenge. Qubits are extremely fragile and sensitive to their environment. Even the slightest disturbance can cause them to lose their quantum properties, a process called decoherence. Scientists have made significant progress in recent years. They have built small-scale quantum computers with a few dozen qubits and are working towards building larger, more stable machines. Breaking the code quantum cryptography. One of the most promising applications of quantum computers is in the field of cryptography. Most of our online security relies on the difficulty of factoring large numbers, a task that is difficult for classical computers but easy for quantum computers. Quantum cryptography offers a solution. It uses the principles of quantum mechanics to create unbreakable codes, ensuring secure communication even in the age of quantum computers. Quantum medicine. Designing life-saving drugs. Quantum computers have the potential to revolutionize medicine. Simulating the behavior of molecules is a complex task that is difficult for classical computers. Quantum computers can simulate these interactions with much higher accuracy, leading to the development of new drugs and therapies. Imagine designing personalized medicine tailored to an individual's genetic makeup, or developing new drugs to cure diseases like Alzheimer's and cancer. Quantum computers could make this a reality. Imagine a future where quantum computers are as common as classical computers are today, integrated into every aspect of our lives. From healthcare to finance, logistics to climate modeling, the applications are endless. As we stand on the brink of this new technological frontier, the possibilities are truly limitless.